Okay, so the topic for today is EKF SLAM. So we looked into the extended Kalman filter last week. I looked at on a more kind of, I don't want to really say theoretical perspective, but more an abstract perspective, not looking into the specific issues that arise in the context of the simultaneous localization and mapping problem. And this week, the goal is to look more detailed into that. To look more detailed into the adjustments we have to make in order to apply the extended Kalman filter in the context of the simultaneous localization and mapping problem. So if you look to the simultaneous localization and mapping problem, again, you're going to build a map of the environment and at the same time localize the robot within that map. And those estimates, the estimate about the environment, for example, the feature location within the environment, and the robot's pose in the environment are correlated, and we have to do those estimations at the same time. So we cannot nicely decouple the process. It's often referred to as the chicken or egg problem because you have that dependency. You need a good pose estimate in order to build a map, and at the same time, you need a good map in order to localize yourself. So if we look to the question, what do we have? What do we want to estimate? What is given to us are the controls of the robot. So U1 to UT, which are the odometry commands, for example, that have been, or the controls that have been sent to the robot, or the odometry readings from our encoders. The second thing we have is variable D. These are observations here, and so these can be observations in the context of the EKF-based SLAM, typically of landmarks in the environment. So, for example, if we drive around here on campus, the trees we may observe are landmarks, and we estimate the relative location of these landmarks given the robot's pose. And we want to use this to build a joint map of the environment. This is a variable M here. And we want to estimate the path of the robot. This is these X, 0 to T. And so we want to come up with a path estimate of the robot together with a map of the environment. So if we look to the overall picture, what are different approaches that have been proposed to address the SLAM problem, there are three main paradigms. So there are some others, but these are kind of the three main lines you find in literature. The first one is the Kalman filter, and this is what we're going to talk about today. And they are, let's say, call it Kalman filter and friends. They are variants of the Kalman filter, like the unsettled Kalman filter, which we will briefly address next week. Information filter and different techniques that all belong to this family of Kalman filter-based approaches. The second main group of algorithms are particle filters, and they also realization of the base filter, but they make less assumptions about the underlying distributions. So, for example, you relax the assumption or drop the assumption that you believe is a Gaussian distribution in the context of the particle filter. And we have graph-based approaches which are typically not treated anymore as a base filter, but as an optimization approach, although there are techniques which try to combine things of both. We'll also build kind of hybrid approaches between those. And as I said, today we will look into the Kalman filter, or especially the extended Kalman filter here, to address the simultaneous localization and mapping problem. Just to remind you what we had done last week, we looked at the base filter and derived the basic main base filter equations. And we can actually write the base filter as consisting of two steps. First, a prediction step, and the second one is a correction step. So in the prediction step, which is the first one over here, what we mainly use our previous belief and then try to estimate the new pose of the robot based on the so-called motion model. And we discussed different variants of the motion model last week, especially the velocity-based model and the odometry-based model. So this tells us, this probability distribution tells us how does the system or the robot's pose evolve over time if I execute a command to the robot. And this gives us our prediction. So this is a new belief, taking into account the motion of the system, but not considering the observation yet. And the second step, which is the correction step, this uses the observation in order to correct the prediction we made in the first round. And this consists of the prediction, so this is the same term over here, these two quantities, And we have here the so-called sensor model or observation model, which uses the current observation given the state in order to correct for the errors we may have made in the prediction, or not the errors, but the uncertainty which typically increase in the prediction step. And so this is done recursively, so the new belief is obtained from the old belief by taking the previous belief, multiplying it with the motion, integrating over all previous poses. So we say, either the robot is at one pose hypothesis, how does this pose move forward? If you put the second position, how will that move forward? This gives us our new belief, and then we multiply this again with the correction steps, so with our observation model, to come up with the final belief. And in the extended Kalman filter, all of those beliefs here are Gaussian distributions. So they're all Gaussian, that's an important thing. And the second thing is the Kalman filter, just to remind you of that, assumed a linear model. In reality, the world is typically non-linear, so what the extended Kalman filter was doing, it was using a first-order Taylor expansion, an approximation, approximating the nonlinear function by a linear function, and using this approximation to do the estimation. So the EKF, how it is typically used in for addressing the SLAM problem, is for online SLAM. That means we're typically not interested in the complete path of the system. We always want to know where is the robot currently given the map of the environment. So we want to build the map of the environment, and we want to estimate where the robot currently is. That means we integrate out the previous poses, so the past trajectory. We are only interested in the current pose of the robot. So based on our estimation process, we are not really interested in where was the robot 10 minutes ago. We just want to know where's the robot now. Okay, so the distinction is clear. We talked about that in the last weeks, but the last 2 weeks. So the change in the probability distribution is that we only are interested in the variable xt over here and not x0 to t, and the map given our observation and the control commands. Just as a very short reminder, the extended Kalman filter algorithm, as we used it last week. So we have 2 steps here. The first one is the prediction step. What the first line does here, it estimates the mean estimate given the transformation so it predicts the new position of the mean, and then does the corresponding update of the uncertainty estimate of the covariance. What it mainly does, it takes the previous pose. These g's here are the Jacobians, so the term that is used to do the linearization and kind of can transform the covariance makings, especially handling the nonlinearities, and then plus the second noise term R. So basically the motion noise term RT is added to the covariance matrix we had before. If you kind of, for the moment, ignore the nonlinearities and assume that these guys here are identity matrices, so have a linear function, and there's no scaling or things like that involved, then simply adding the term RT simply increases the uncertainty of the system based on the motion uncertainty. So if I'm very, very certain how I move, the values here in this matrix are typically very, very small. So there's a small uncertainty. And then the increase of the overall uncertainty is also small, because it's just an additive term. These matrices are added up. If I have a high uncertainty in my motion, the elements here in this matrix are, especially the diagonal elements, are typically very large, and this leads to a significant increase in uncertainty. Of course, this term here only affects the pose of the robot. So just by carrying out a motion command, I don't want to change the uncertainty about or the landmark locations. This only affects the robot's pose. So you have to take care of how this RT looks like given the dimensions we put into our mean estimate. So that was the prediction step. The next 3 lines from 4 to 6 correspond to the correction step. And what is done here, the first line, line 4, computes the so-called Kalman gain. This can be seen as a weighting on how much do I trust my observations relative to my motion. So if I do not trust at all my the motion estimates, if I fully trust my prediction, so my motion model, and I do not at all trust my observations, then this matrix K here will be very small. Because this results to the fact that the new mean is basically the predicted mean I had before. And the more I trust my observations, the more this Kalman gain K is different from 0. So this is, and it's basically used to compute the uncertainty I had before of the predicted uncertainty, and takes into account the uncertainty of the observations, which is here given by this matrix QT. And what this term over here corresponds to is the observation we obtained, ZT, minus the predicted observation, given the current state. So given the current state, we can say I should observe this landmarks relative to the robot's pose, for example, 2 meters to the right-hand side. But I observe it, in reality, 1.5 meters to the right-hand side. So this is the difference between the expected observation, this term, and the obtained observation. And the more they are different, the bigger is the correction I do. So if they are perfectly in line, if ZT and the expected observation are exactly the same, means they are 0, I keep my, my predicted mean. The more they vary, the bigger the update I do. And then the second term is the corresponding change of the uncertainty, the covariance matrix here, and here the Kalman gain is again involved. And so if I trust my observations a lot, the uncertainty typically decreases in the estimate I have here. Okay, so let's look to EKF SLAM. Let's apply the EKF to the SLAM problem. So when I estimate the robot's pose in the environment, as well as features, and we assume here that we have known correspondency. That means if I observe a landmark, I know to which landmark this observation corresponds to in my belief. So I can perfectly distinguish all the landmarks. So this is a very strong assumption, but we make that assumption for the moment because otherwise we would have to take into account all different potential data associations we may have, which makes the problem very quickly very complex. So we assume here a known correspondency. So if I observe something, I say, I know this is landmark number 1, or this is landmark number 2. So the state space we are considering is xt here is a 3 plus 2m dimensional vector, where the 3 dimensions are for the robot's pose, so it's x location, it's y location, and its orientation theta, plus 2 dimensions for every landmark, because in this example I want to estimate the xy location of the landmarks in the space. So if I have n landmarks, I have here 3 plus 2n dimensionality of the field. Okay, so now this is the way the state looks like. How does the covariance matrix look like if this is my state?
First tree is your x, y, theta position of your robots, and the two, and then there is a part which is the correlation between different landmarks, and the diagonal is the uncertainty about different landmarks and the position and the theta.
Exactly. So it should look something like this. So here again we have our mean, and this part here corresponds to the covariance matrix. And you can actually write this covariance matrix as consisting of 4 blocks. The first block is the yellow block over there, which corresponds to the uncertainty about the robot's pose. So it says what's the uncertainty in x in there's a typo, that should be a y here. Let's see that. And theta, as well as the cross correlations between them. Then we have the blue block down here, which is the uncertainty about the landmark locations. We have here on the main diagonal like this one. And then we have also the off-diagonal elements, which tell me the correlations between the landmark locations. So if I know, for example, the pose of landmark 1, how does this impact my knowledge about the location of landmark 2? And then we have this green part over here, and they correlate the knowledge about the robot's pose with the knowledge about landmark locations. So given I know where all the landmarks are, I typically have know a lot about where the robot is. Again, if I know where the robot is, you can estimate the landmarks better. It's going to be 4 different blocks. Okay, and these two, the green blocks, are the same except the transposition. Okay, so sometimes we find it written also this way. XR here is now the robot's pose, 3-dimensional, and landmarks, and then here all these elements are now small covariance matrices. So these are 2x2 matrices, these are 3x3 matrices, and here we have 2x3 matrices.
How do we calculate the single elements of this?
We will come to that in a second. So you will see that. So we go to all different steps of the EKF, and we will actually come to all those elements. Tell you how you actually compute all the individual elements.
There is a function which is the robot moving, and then you do some partial derivative on this function.
This will everything. So the updates of all those elements is just done using the equations in the EKF algorithms. There's no other black magic we put in there. Everything results from applying the EKF equations. Also, sometimes you even find more compactly written. So that this is a 3-dimensional vector, a 2n vector, and the individual uncertainties here. So take care about notation. Some people write XR to refer to the robot's pose. Some use XT for time step T. Sometimes it's only X. So you have to be a little bit flexible. That X corresponds to the robot's pose. Sometimes it's the X dimension. Sometimes it is the full pose. So I try to be consistent in the slides, but depending which material you look up, you may find small inconsistencies. But just to avoid all the different indices we have to put here. Okay, so what are the key steps in our EKF if you want to use it for the SLAM problem? So what's the first thing we need to do?
Initialize.
Yeah, of course. We need to initialize it first. That's completely fine. So we need to initialize x and theta. Once we have done that, we get our observations and our commands. What do we do? First step.
Prediction.
First thing, the prediction. What we then need to do is we need to compute the predicted measurements. So what are we expected to observe? And we need to take our measurement and compare those two, which also involve the data association. Signing that we now for the moment assume that we know the data association. And then we do the update step. And then we continue this process. Okay. So, sorry. Yes, please.
On the prediction step, we're not going to predict anything in the map, right? Because the map is static.
Yeah, so the map is assumed to be static, so we assume that the environment doesn't change. We have to predict the new pose of the robot, and this also changes the robot landmark correlations. But it doesn't change the block about the uncertainty of the landmarks.
Sure. Okay. So we're not increasing the uncertainty in.
So if you so we have our x, y, and x and the landmarks, just to be compact. What the prediction step does for the mean, it only changes this variable here, and it leaves m unchanged. So if we execute the odometry command, we only change the pose of the robot, not the position of the landmarks. This, however, based on the Jacobian we use, hasn't, or what it impacts in the uncertainty in the covariance matrix. So we have here about the pose, about the landmarks. So what the update changes in the prediction step here, it first changes the uncertainty about the pose of the robot. It leaves the uncertainty about the landmark locations unchanged, but it also updates the correlation between the robot's pose and landmarks. So first, I would like to go to a small illustration of these individual steps, and then we go to every step individually. So again, to visually state what's going on, we have the robot's pose, our initial uncertainty, we execute our motion, so we end up being here, and we have increased the uncertainty about the robot's pose increases based on the uncertainty of the motion. And we have our estimates about landmark location. So what changes is always shown in green here in our state estimate. So as I said before, what I've written here on the blackboard, is it changes the pose of the robot, the x, y, theta, instead of the mean, and it changes the corresponding uncertainty together with all cross correlations between the robot's poses and the landmark location. It leaves the uncertainty about the landmarks itself unchanged. Because I just move, I don't change anything in the environment. Okay? Okay, the next thing is we have to predict our measurement. So this is the current pose of the robot, and this is, here we know, our map tells me there's a landmark, so I say, this is my predicted observations, my predicted observation. Now we look to the observation I obtained, it may be slightly off to what I predicted my measurement. The reason for that is simply that my current pose is not the mean. And I have some uncertainty in my observations. But if my observation would be perfect, this would mean that that the robot is currently not at the mean or the filtered estimate of the mean. But of course, we have some uncertainty in the prediction, and therefore we have we obtain a measurement which typically does not correspond to the expected measurements, even if the robot's pose is exactly at the mean. Okay, then we make our data association, so we have to say, okay, this landmark actually corresponds to this landmark, and the difference between those is the term which is used to update the mean, kind of the innovation we have in there. And then we compute the update step, and the update step actually changes everything in the filter. So it updates the location of the robot and the location of all landmarks, and it typically changes all elements of our covariance matrix here.
And the question is about the previous step. How do we do this data association if we have only the position of the landmark and no labels which can do that?
So there are different ways to do that. So one thing is to, so perhaps we are in the lucky situation that our sensor provides some hints about that. So we have a vision sensor, there are ways for extracting or for identifying by estimating the appearance of objects, my landmarks. So there are different kind of visual features I can use, which are not perfectly distinct, but which give me a pretty good estimate if two things are the same or not. There's one thing. If we are only in a situation where, let's say, we have a laser scanner and estimate the position of the trees, we may use the radius of the trees, of the trunks of the trees, as a way for saying a small tree is not likely to be matched to a big tree. Maybe all trees have been planted approximately at the same time, though they're all of the same size. There may be the situation that they're completely indistinguishable. Then what we typically need to do is to make some assumption that we say, we typically say the observation we get, we assign it to the closest landmark in our map, based on the kind of real physical distance, Euclidean distance between them, and also taking into account the uncertainty we have of our estimate. So we know a position of a landmark very, very accurately. So we have a very small covariance matrix. Also, the observation is close, but it's much further away than what my uncertainty tells me. I may even reject it and say it's a new landmark which I haven't observed yet. So this is what's typically called the nearest neighbor data association. And you typically have some kind of gating function in there, which is typically done based on the locus distance, so taking into account the uncertainty of the landmark and the observation I have and the uncertainty of the observation, and saying this is possibly one, so this observation possibly corresponds to a certain feature, or if it's too far away from anything I've seen so far, I say it's a new landmark. It's kind of the standard strategy that we can use. The problem is data association errors can lead to inconsistent estimates. So if we do wrong data association, it obviously leads to a wrong estimate that we obtain of the environment. On the other hand, tracking all possible data associations is very complex because you have a huge tree of possible data association which expands, and for every kind of node of this tree, you would have to maintain an own Kalman filter. So it gets very, very costly very quickly. And that's the reason why most people just do a nearest neighbor data association, or they have some feature descriptor based on the sensor tells me this trunk looks gray, this trunk looks more black, so maybe different trees, something like this. But this is so treating this in a very general way leads very, very quickly to the problem that you have a huge number of possible data associations. It's computationally intractable to maintain all of them. And so you have to make, typically, you have to make approximation in this context. Any further questions about that so far? Okay, so let's get more concrete and dive into the individual steps of the Kalman filter and see what happens here. So we assume the robot moves on the plane, so x, y, theta. We assume we have a velocity-based motion model, so we have no wheel encoders. We just command translational velocity and a rotational velocity to the robot's hardware. The robot tries to execute that as good as it can. We assume that the robot observes point landmarks. We have a range bearing sensor, so a sensor which tells me the distance to a landmark as well as the angle where I find it. So consider the example of a robot with a laser scanner observing trunks of trees. The trees are, so we don't extract any certain feature, we just assume we have a data association module which gives us the perfect data association. So we say data association is perfect, and so we have known data association and known correspondences. And we, for the moment, just to make the implementation here a little bit easier, we assume that we know the number of landmarks which are in the environment. The reason for this is following that I can directly initialize my mean estimate and my covariance estimate, and I don't have to deal with changing dimensionality of this matrix if I know the number of landmarks, because I know kind of the size of this block. How do I initialize it? Say, I don't know anything about it, so the only thing I know, I start up the robot where it currently is, and I say this is my reference frame. But currently the robot is at 0, 0, 0 in the robot's own reference frame with 0 uncertainty. You can see this by the first 3 elements being 0 of the mean vector. This is the x, y, theta. And this matrix here, the 3x3 matrix consisting of 0 blocks. I perfectly know where the system is, so no uncertainty, but the robot is. But I don't know anything about the landmarks. So this block corresponds to landmarks, and I simply say I have an infinite uncertainty of the individual landmarks. So if I look to all the diagonal blocks, I say I have an infinite uncertainty in the x location of a landmark, I have an infinite uncertainty in the y location of a landmark. And so I even estimate the means with 0, but infinite uncertainty. So I initialize it. If I would drop the assumption that I know the number of landmarks I have in the environment, that would simply mean I will start with a 3x3 matrix here, and a 3-dimensional vector here, and as soon as I observe something new, I would have to extend that, the mean vector and the covariance vector. But let's ignore that for the moment, although implementation-wise, it's not too difficult to do that, but it's a little bit harder to write things down. Okay. So let's revisit the individual steps of the Kalman filter, and let's go through every individual line of the Kalman filter and see what happens there. So the first thing is we have to update the mean. So given my nonlinear function, which describes me the motion of the robot in the plane, I want to make a prediction about the new mean. We looked into that last week, briefly explained the motion model for the case of having no wheel encoders, so the velocity-based model for a wheeled system. And we had this equation over here, which says the new pose, just considering the first 3 dimensions here for the moment, x, y, theta, is the old position plus this term over here. this term just tells me, so Vt is the translation velocity, omega t is the rotation velocity, and I obtain this equation, these equations over here, which tell me where does the robot move, given the translation and rotation velocity and coordinate orientation. So you can just make a prediction based on motion commands. So this whole function is this function small g using the odometry ut. The odometry is the translation velocity and the rotational velocity, and the previous state. So here I've written it as g, x, y, theta, just to indicate that this is only the part that corresponds to the robot's location, not to the landmarks. But in my Kalman filter here, I need to do this, specify this function g for the full state vector, not only for the x, y, for the 3 dimensions. So how do I have to change this function g, x, y, theta to obtain the real g, which works in the high dimensional space, in the 3 plus 2n space? Exactly. How can I do that? How can I do that? If I write that down as a function.
Operators, when the value you pass to this g function should consist all the landmarks and the vector for all the landmarks and
the
so
position
of the robot.
We'll have the landmark locations here, the old ones here, and they don't change. So it's just kind of the identity between all the rest. So just add the landmark location here, and I add 0 elements. Okay. Typically, I do that by using typically in matrix form. I use one of those matrices. They're called here F, and they consist here of a 3 by 3 block, which consists of the identity matrix, and then 2 n columns which are 0. Because if I do that, how does this function look like? So I have my f, which is equal to 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, and all zeros here to n. And so this is my function n, my function f. And if I now have to write f times my vector, which is right of g, x, y, theta, so it was x, y prime, theta prime, so the updated values. And I multiply it by this matrix transposed. What I obtain is 1, 0, 0, 0, 1, 0, 0, 0, 1, and then here a couple of zeros. And multiply it with 3-dimensional vector x prime, y prime, theta prime. If I do that multiplication, what do I obtain?
X prime, y prime, theta prime, 0, 0, 0.
X prime, y prime, 0, theta prime, 0, 0. So multiply these 3 dimensions with these 3 gives you the first element, this time this gives you the second element, and so on. Simply all elements, all multiplications below you have the 0 elements here. So this is what you have done. So therefore we can use this function f to map kind of our low-dimensional update of the individual components to the high-dimensional space. And this whole thing gives me my function g. Okay, so this part is done. I know how to update all elements.
Where is the uncertainty here?
So far we've just done the mean. We just did the mean, the first line, no uncertainty.
Some noise ceremony.
Yes, so this comes in the second line of the prediction.
For me, there is no noise.
I'll just say, I just have my predicted observation and I propagate the mean according to my transformation. Okay, so the second thing is, we have to execute this one. So we know this is our previous uncertainty we have, so we know that. RT, we also assume to know this is the uncertainty of the motion I have. So the only thing which needs to be specified is this matrix G, the Jacobian of the function. A question or anything unclear? Okay. So what we need to fix is this G. How to obtain the G?
You just you get the derivative of the function.
Exactly. So we just need to derive the function G, small g. Okay, let's have a look to that. So again, we can do that since we only want to change the elements, or we only want to take into account the function G only manipulates the x, y, theta location of the robot. So we can actually split that Jacobian up into a 3 by 3 matrix, which I call Gx of t, with x here indicate that it only affects the robot's pose. And there's no change in the landmark locations. It's a perfect my linear function with the identity matrix. So every kind of small perturbation I do to the landmark pose maps 1 to 1 in this linear function to the update. So this is an identity matrix. Is it clear why I can do that? Clear to everyone? If not, we can derive it.
How do you obtain the GST?
Well, that's what we do next here. Just because to avoid, the only thing why I do that, what I want to avoid is here writing down the Jacobian on the blackboard of 3 times 2n by 3 times 2n dimensions. So we can say these elements we can fix by just thinking about it, and then we have just to derive this matrix here, which is a 3 by 3 matrix, which is easier to do. Okay? Okay. So let's do the typical way. I obtain a Jacobian by taking my function, and every individual block in here is the partial derivative of the first part of the function to the first element to x, then to y, theta, the second line of my function g to x, y, theta, and so on. So it's partial derivative towards x, y, theta of this function over here. So if I take the partial derivative of this block over here, the first part, this is a sum, what do I obtain? Yeah, the identity matrix. So if there are 3 dimensions, if I derive this term by x, it gives me a 1. If I derive it by y or theta, it gives me 0, with the corresponding 1 here. So you can actually write this as the identity matrix into the 3 by 3 matrix, this identity over here, 3 by 3, plus the partial derivative of the rest.
What about times x, y, theta in the second part?
Sorry about?
Because you have a sum, right?
Yes. So this again stays a sum. So there's a sum of 2 terms.
Sorry.
And I compute the derivative, and I can do that by computing the derivative of the individual terms and summing them up. Okay, so this is a 3 by 3 identity matrix over here. Now we have to compute the partial derivatives of this block over here. So what do I obtain if I derive this term towards x? First line over here. 0. If I derive it towards y, also. What about the second line? What about the second line if I derive this one to x or y? Same, and for the last one as well. So the part of this matrix, of this partial derivative here, is pretty easy, which is 0 in x, 0 in y, 0 in zeta, and 0, 0, 0 for y as well. So it was easy. The little bit more difficult part comes to the game, how to derive this line toward theta. There's a sign in there, sine, cosine, and the corresponding signs in front of it allows you to compute this. And if you do this, you end up with this term over here. So cosine, the sine changes to the cosine, the first derivative, and the cosine to the minus sign. And the exact calculation you can actually do is one of the exercises. You can manually derive that, but that's not that tricky. So this is the term we have. So we can actually write this as 1, 1, 1 here, and these two elements which are not. Okay? So this is our function j. So nothing very special happened in here, except that I just derived manually the individual elements of this nonlinear function, small g. Okay, so now I have that, and I can now compute this term over here. So the gt is gt index x over here, and this 2n by 2n identity matrix over here, multiplied with the individual elements of my, the individual blocks of my covariance matrix, and then the same term here transposed plus RT. And if I do these two matrix multiplications, I add up here with GTX, theta XX, theta sigma XX, and the transpose of the Jacobian. And here in the off-diagonal elements, I have the product of the Jacobian times the cross correlations, and this term stays the same. And this exactly corresponds to the term we had here on the blackboard, where I told you that the prediction step updates these three parts of the matrix and leaves this one unchanged. And here on the slide, you exactly see in which way they are updated. So the important thing to note in here is that the prediction step is can be typically executed quite efficiently in the Kalman filter, because if you look to not to the EKF in general, but the EKF in the SLAM case, the reason for this is that this term down here, which we don't change, is actually the big matrix, because it contains all the landmarks. This guy here is just a 3 by 3 matrix, which we can manipulate very quickly, costly operations which are done here on this matrix, because this is a 2n by 2n matrix. If I have millions of landmarks, it's maybe 2 million by 2 million dimensional, 2 million by 2 million matrix. Therefore, operations on this term are expensive. The other ones, the others one are cheap compared to this block over here. Therefore, the prediction step in the EKF SLAM is something we can typically do efficiently. More are the update step, where the whole matrix gets changed. Okay, so I just need to do these, execute these operations, and then add the noise term RT. And here, again, RT, which form has RT?
Can you repeat your question? Repeat it again, please.
So, sorry, how does RT look like?
Let's say 3 by 3 matrix and then loads of zeros.
Exactly. So it has, the first block is the 3 by 3 matrix. This is the uncertainty which is added to the robot's pose, increased uncertainty. And there's simply no change in the uncertainty of the landmarks. Just because the robot moves, it doesn't change my belief about where the landmarks are. Right? So the rest is 0. So this RT has a 3 by 3 block which is non-zero, and the rest is 0. Okay?
There's no question about this.
Sure.
RT. In the motion model, when we just want to plot the uncertainty, we end up with something, a banana shape, because we have many uncertainty. But here, look, we have only one
Exactly. So
uncertainty.
the thing is, in the models I presented in here, I showed that kind of banana-shaped distribution which results from executing these motion commands, is the distribution you obtain if you really conduct those steps. In the EKF, we have the issue that everything has to be a Gaussian distribution. It's the assumption we have in there. Therefore, this term gives me a regular covariance matrix, not because the Gaussian is not able to take into account the banana shape. The model is clearly imperfect. It's not perfect. I just have linearized my nonlinear function to propagate my belief through that linearized function, which is definitely not exactly what happens in the real world. So it's clearly the case, you're right, this doesn't give me a banana-shaped distribution. The reason for this is the EKF can't handle it. It has to be a Gaussian again.
And we are only uncertain between two different posts here. I mean, at the predictions. We are in the x1 or x1 plus something.
Yes. This is always, all the base filters do that in this incremental way. So you have one motion which gives you some small increase in uncertainty. If you accumulate that over time, it really gives a real banana shape. If you really, let's say, if you take a robot and you execute 100 times these motion commands, you will end up in having something which is very, very similar to a banana shape distribution. But this is nothing the Gaussian distribution can represent in here. At least the Gaussian in the xy or in the xy theta space we have in here. So it's clearly the case it's an imperfect model. And simply, we can do better, but if we build up a better motion model, we don't have a Gaussian distribution anymore, and we can't apply the Kalman filter.
And when we iterate through this extended Kalman filter, each time we have only a new uncertainty, and we don't care about these previous things. And we do.
No, so
because the R is constant 3 by 3 something.
So yeah, so the RT, I mean, it has a time index t. Depending on the motion you command, it may be different. So if you move very fast, for example, your uncertainty may be different.
You will also update R here somewhere.
No, so R is something you assume to be given. So you know the model of your robot. So for example, if you move very, very fast, you know that you have a higher uncertainty compared to the fact that you move very slow, for example. This is something which the system assumes to be given, this RT matrix. This is something which, because it's inherently dependent on your robot, there's nothing you can really estimate here. It's something you say, this robot design has a certain error.
But subscript T, it looks like we have a different noise value in each time step.
This can be the case if you consider what I said before, if the noise value depends on the motion command you execute. Okay. So you have that, for example, in reality, if the faster you drive, or the more you accelerate, the more likely is that your wheels slip, and the more noise you typically have in there. Or if you typically drive on a straight line, so steering both wheels in the same speed, to be a pretty accurate motion. If you do weird turning maneuvers, again, you increase the risk of slippage, and then the uncertainty may be bigger. So you may really adjust this term depending on the motion command you execute, but this really depends on the robot you're using. So this is something robot specific that you have to provide as an input to the system.
Sorry for that bothering.
Go ahead.
Could you speak up, please?
Yeah. Okay. Louder, you mean?
Yes.
Yeah. The problem is the ellipse shape is going to bigger and bigger, as you mentioned in previous slides. But here is the noise term, something constant. But how does it come?
So the noise term RT here, so we assume it to be constant over time, but we simply always add that to the uncertainty we had before. So the question was, if this is constant, why does the uncertainty increase over time? The reason for this is, at every point in time here, I add the matrix RT to my estimate. So in every point in time, I add a new noise term, so the noise increases, the uncertainty increases and increases, not the noise uncertainty. Because in every point in time, I add the noise term, so it increases my uncertainty overall. Okay, so these prediction step is done. Are there any questions about the prediction step at the moment? Okay. So we can actually write this now in an algorithmic form. So we have our matrix F X, which does this mapping from the low-dimensional space to the high-dimensional space. So we can write the mean update is the new mean is the old mean plus this matrix transpose time the terms here of the velocity-based motion model as we have written it before. We can compute the Jacobian, it's an identity matrix, plus this same matrix Ft times Ft, which maps it to the to this huge matrix of dimension. So this matrix here has a dimension of 3 plus 2n times 3 plus 2n. And then we have the corresponding update, is just the plain formula here. And sometimes you find also written in this way, so depending if you write RT as a 3 by 3 matrix or RTX the rest is 0. Use exactly the same function to map it to the high dimensional space. So this is the part which are the EKF SLAM prediction step. Any questions about that? So in the exercise, you will have to implement such a system. So if you have any questions, it makes sense to ask a question now. Okay. Okay, extended Kalman filter. Next step. Again, we have our equations here. We assumed Qt to be given because this is the uncertainty in our sensor. So the only thing we actually have to do is actually compute this matrix H of the Jacobian of the of our measurement function, and we also have to look into this function H to compute the predicted observation. So again, to remind you of that, we assume to have known data association. So let's be CT. It's often written in this way that you say CT I equals J, which means the ith measurement at time step t, because you may observe multiple landmarks, corresponds to the landmark with the index J in your filter. So let's say J is one of the landmarks in your belief. For example, J equals 1 is the first landmark, so it means the 4th and the 5th dimension in your mean estimate. And you say this is exactly the landmark which was observed. For example, at time step t equals 1 and the first measurement I equals 1. This is really what you call this correspondence variables. The first thing we have to do if we obtain an observation and we don't know anything about the landmark, we need to initialize that. And the good thing to initialize it is to use the observation we obtain to initialize the landmark pose. And the reason why we have to do that is because we need to linearize our function, our measurement function, at the current estimate. And if you keep it at 0, 0, 0, we may be very, very far off. So if you would have we would be in the linear case, this initialization wouldn't be needed because one update in the linear case, just subtracting 0, 0, 0 by what I measure, would give me what I measure. But since we are in a non-linear case, we need to linearize our function. We need to take that into account. So we need to initialize the landmark if it is unobserved. And then what we do, we need to compute the Jacobian of H, our measurement function, and then we proceed computing the Kalman gain, updating the mean, and updating the covariance matrix. Okay. So we assume to have a range bearing observation. That means at every point in time, our dt of the ith landmark I observe at every point in time is given by a two-dimensional vector. The first dimension is the distance, r, so the Euclidean distance to that I measured to the landmark. So if I measured that wall, it would give me 4 meters, for example, would be the first term. And phi here gives me the angle in which I measure it. So in this case, it may be 90 degrees. I'm looking in this direction. So the observation I would obtain would be 4 meters, 90 degrees. Okay? And I get that for every landmark at every point in time. So how to map that to the estimation, to our reference frame that we assume the landmark is in our global reference frame. So to say the x dimension of the landmark J, and this is the y dimension of the landmark J, is given by the current robot pose, because we always have these relative observations. This is the first term over here. And then we have that relative measurement over here. And this is given by simple sine and cosine that depends on the current heading estimate that the robot has. This is multi theta, so just the theta dimension of that, so my orientation, plus in the direction in which I measure it. So if this is in my global reference frame, for example, so if this is my global reference frame 0, the orientation 0, this may be plus 90 degrees. And if I measure it here, this would be again 90 degrees. So that would be the cosine of 90 plus 90. So this gives me this term, and multiplied by the range measurement. And this gives me the position of the landmark where I assume this landmark to be given the robot's pose and my measurement, knowing nothing but the landmark before. Kind of clear? Okay. So the same equation that you may use to use laser rangefinder to estimate the endpoints of the laser scanner. In case you have done that in one of the previous courses or practical stuff. Okay, now we have a few terms which we use in here. So we have this delta over here, which is just a difference in the x and y location between the robot's pose and the landmarks. So it's just the robot's pose and the landmark location, the difference in x and the difference in y. This is delta, just a variable I define. And then I can define q as the product of these two vectors, the dot product, and so I obtain the Euclidean distance. Squared Euclidean distance. These two features. This is the difference in x, the difference in y, and this is the Euclidean distance. If I use this abbreviation, this delta and this q's, I can actually write the predicted measurement, where I predict the measurement to be, for my belief, as the square root of q, because this is the distance I measure. This corresponds to the r term in my observation. And the a tan 2 function, again, which tells me the orientation where I should observe that landmark. So I take the belief where the landmark is according to my mean estimate at the moment, and where the robot assumes to be. I subtract those two values for x and y, that gives me delta, just based on the current mean estimate. And then that head gives me the predicted observation. So as an example, considering you have a state vector, example, and it's, for example, 1, 2, 0, 1, 1. Nothing else. So this was the robot's pose, and this is the first landmark. So this is my current, this is my estimated mean times the t. Then the delta would be difference in x, so the position of the landmark in x, which is this one over here, 1 minus 1, and same for the y, 1 minus 2, 1 minus 2, so this is 0 minus 1. That would be delta. Q, as a result of that, would be 0 times 0 plus minus 1 times minus 1 would be 1. So, as a result of that, that head of t would be the square root of q, the square root of 1, so it's 1. It's exactly the distance to the landmark. And then the a tan of the a tan 2 of the difference in y and the difference in x, so it's minus 1, 0, minus the coordinate orientation of the robot head was supposed to be 0, so it'd be a tan of minus 1. Okay? So based on my current belief, with this equation I can compute the expected measurement. Given the belief I have, I expect to get this measurement. If my belief is perfect and I have no noise in the observations, this is what I should obtain. Okay? Okay. So we have the predicted observation. We know what we observed. What's missing? The Jacobian. So we need the Jacobian to do the completely Kalman measurement. Okay, can do that. So this was the quantities we had before. How do I compute the Jacobian? Again, I'm considering here what I call H low, because again, this low dimensional Jacobian, not going to the full space, because I only observe a few landmarks. I don't observe everything. If I would observe everything, so if I'm in a position that can observe every single landmark, this guy would again be here a high dimensional term, so I just call it low because I have assumed here in this case to observe only one single landmark at a point in time. Okay, so I have to derive the function h, my measurement function, with respect to the current mean estimate. And again, here I look only into the dimensions which are with respect to the robot's pose and the position of the landmark. So their first three terms here the derivative with respect to x, y, theta, and then with respect to the landmark's pose. So it's again, in the prediction step, the function g was only updating the robot's pose. And here, so all other derivatives, so it just had this identity matrix in there, not any change. In this case here, it affects only the landmarks I observe and the robot's pose, because all other elements should be 0. And if I derive this function h, I end up with this matrix over here. So it's a 2 times 5-dimensional matrix for a single measurement. If I would get more than one measurement, I would need to stack those matrices to get a bigger matrix. So the exact derivations of this function you also do in your exercises, so I don't go into the individual blocks, but that's, again, with a few lines can be done. It's not really like magic, but this is something which everyone should actually do on its own. So then I have my Jacobian. Again, I use one of those matrices F to map that again to my original space, because in the end I need to update my full covariance matrix. So I need this function F to transform H into a high-dimensional space. And this can be done in the following way. I have this matrix. I have again an identity block here for the robot's pose. This block is 0, 5-dimensional, 5 rows. And then we have a number of columns which are 0 until I have the 2 times, so the i's, the 2 columns which corresponds to the j's landmark. So this is a landmark I observe. So if I, for example, would have, this would be the 3rd landmark, just as an example. This would be 4 columns, which would be 0 for the 1st landmark and 2nd landmark. Then for the 3rd landmark, I have the 1 and 1 here. Then I have again zeros for all other landmarks. So multiplying this with these low-dimensional Jacobian we define maps it to this higher-dimensional space. So if we have, if you look at the dimensionality of our matrix H, so we have H low was 2 times 5 for one single observation, 2 times 5. And this matrix F is 5 times what? Dimensionality of this matrix is n plus 3. Exactly, 2n plus 3. 2n plus 3. So the product of both of H low times F will lead to a 2 times 2n plus 3-dimensional matrix. And this maps the current state vector, or the current state, to an observation. Okay, now we have H. H is known. Well, these terms are known. This is known, and this is the uncertainty, the covariance matrix we had before. So you can just execute this, computing those matrices by multiplying matrices and actually inverting this term over here. So to the power of -1. And then we have computed the Kalman gain. Again, nothing very special happening here. Once I've defined this matrix H, this is just executing matrix multiplications and an inversion of the matrix. So one block one shouldn't forget is, what's the cost of a matrix inversion computationally? Sorry?
N to 2.4.
Yeah, so it's in the kind of standard case, it's cubic complexity, n to the power of 3. And nowadays, state-of-the-art methods are at n to the power of approximately 2.4, 2.39 something. So this operation here is costly term, this inversion. What's the dimensionality of this term? So we said H is a 2 by 2n plus 3 matrix.
Same as the observation.
So it's the same as the observation. If you have just consider one single observation at a time, it doesn't really hurt us. Versus if it's two-dimensional observations, this term here gets a 2 by 2 matrix, which I can easily invert. If I have more observations I see at the same time, this changes, gets more costly. But as long as I don't have a sensor which observes the whole world, actually often do not really care about that term. Because typically I have a sensor which just sees locally what's around the robot. So it's always kind of bounded by the visibility what I can observe. So it's not that this matrix can grow and the dimension of this matrix can grow and grow and grow, and so the inversion gets a super costly operation. This is not the case as soon as we move to kind of reasonably sized environments and have regular sensors. So if you have a sensor which always observes the whole world, this is a super costly operation. But this is not the case in reality. So in the reality, although this can introduce a cubic or near cubic complexity, this is only affected by the dimensionality of your measurements. And so this is a thing which doesn't dominate the Kalman filter. What it practically dominates the Kalman filter for in the SLAM context is this quadratic matrix where all elements get updated. So if n squared elements in this matrix which gets updated, and this leads to a quadratic complexity in the number of features we have. Okay, and now it's just everything is straightforward. All these things can be obtained. Here, just execute my function h, which I described before. So how to map from the space of observations to the predicted observation. This was exactly how this was done. How to compute the predicted observation from the state. So h was defined, and everything is just straightforward math, just matrix multiplications. So that's it. We're done. You can return the mean and the covariance matrix. Okay. We can also write this as an algorithm. So assume we have our matrix Qt for a single measurement, and we have so we have an uncertainty in the range and uncertainty in the clearing estimate. So what we do is we look to all observed landmarks, to all observed features. These are the individual observations we obtained, and let's assume that we have this known correspondency, so that someone tells us, some oracle tells us, to which landmark does this observation corresponds to in our mean vector. This is a j, our local variable j. What we then do, if we have never observed the landmark, we need to initialize it. And we initialize it with the inverse measurement function. So given I know where the robot is, and given where I assume it to be, I compute the post. And this step is only needed for the linearization in this H matrix. So if we would use the linear Kalman filter and we would have a linear function, this step wouldn't be needed because it just takes the difference between 0 and my original measurement, would update it accordingly. Here, since we use the EKF and the linearization point depends on the current position of the mean vector. So this updates the mean vector, and the linearization depends on the mean vector. I have to initialize it in this way to get a better linearization. Then I compute the predicted observation exactly as we did it before. This delta and this q, and this gives me my predicted observation. And then the next step, I build up my large matrix F, which again maps my low-dimensional H matrix to the high-dimensional space. Then I compute this HT, and then these are the 3 steps exactly as in the Kalman filter equation, only that this H function is here already replaced by that hat, the predicted observation. That's it. I'm done. I do that for every observation, and I'm done. So So this is one way of implementing a Kalman filter. So what was done here, especially we had this this loop where we iterated over every individual landmark observation. So I took landmark observation 1, updated the filter. Landmark observation 2, I updated the filter, and so on. I can also do this in one shot. Building a larger H matrix where I say simply I've observed 10 landmarks, every observation is 2-dimensional, so I have 20-dimensional state here. So what would you imagine to be the differences between doing the update in this way, so one landmark at a time, or doing the update once for all observations? So there's no difference in what you calculate, but it can have a practical application in terms of speed.
You can use parallel computing.
Okay, but you kind of ignore that. Just say it all one core CPU. But the main reason comes from the fact of this matrix inversion. In one situation, I have, if I get, let's say, I observations at one point in time, I have to do I inversions of a 2x2 matrix, or I have once to invert 2i-dimensional matrix. Once inverting a 2i-dimensional matrix is more expensive than doing it I times a 2-dimensional matrix. The problem I, however, have is I have to make this update of the mean and the Kalman gain, updating the mean and the covariance at every point in time, so it's quadratic. So once I just have to do it once, and once I have to do it I times. So once the inversion is more expensive, and the update is cheaper, and once the other way around. So it simply depends on the dimensionality I have. If I'm typically doing this in the context of SLAM, it's actually better to stack all those matrices together, just invert it once, and then do the update, because typically n can be pretty huge, so the dimensionality of this matrix may be large. But sometimes kind of easier to understand if I do one matrix, one observation at a time, and not all observations at the same point in time. So there are two ways for doing this. If you're going to implement that, what you hopefully will do for the exercises, there are two things you need to take care of. First is always normalize the angular component, something which is completely ignored here. But the angular component has this wraparound. You kind of linearize a function, and the linearized version doesn't know that whatever 2 pi equals 0. So you may have to get big update steps in the orientations, which are quite likely to screw up something in your system. So always normalize your angle. So always normalize it back to whatever minus pi to pi or whatever you use. It's a practical implementation here. The other thing is, if you use Octave to do that, you do not need to create these F matrices explicitly, which maps you from this low-dimensional space to this high-dimensional space, because in Octave you can directly address parts of your matrices or blocks of your matrices with just the corresponding indices. So you can even write it sometimes easier in Octave than I did it here on the slide, because you don't need this transformation between those spaces. You can directly write in the corresponding blocks of your matrix. So it can make it easier for you. Okay, perfect. Done. So I hope everyone of you is able to implement basic vanilla EKF SLAM system with known correspondences using what we've done here. This is something you will have to do as your homework. So the homework sheet, which are actually here, so you can just distribute them, please. They consist of kind of 3 exercises, and one of them is the implementation. For the implementation, you have 2 weeks' time. For the rest, just hand it next week, because just some people may need some time to get into Octave. Also want to give you the chance to work on that and then ask questions in the next exercise again. So the third exercise, you have 2 weeks' time to complete that. For the rest, 1 week. That's kind of the schedule. Okay. So we've done now the basic math for EKF SLAM. So let's look a little bit into the properties of such SLAM systems and how do different operations in this EKF SLAM updates, for example, affect the filter. How do observations affect the filter more from a practical point of view? The first thing, which is important not only to EKF SLAM but to SLAM in general, is what we so-called loop closing. Loop closing means recognizing an area where the robot has been before and kind of returns. So you drive around here on campus, let's say you nicely map this area around here in front of the building, you move around that side, around the building, and re-enter this area here from the George Köhler Allee. So you will re-enter an already mapped place. You have to make this association. Where am I given the model I built so far? And this is what we so-called loop closing. This can be seen as doing a data association with some high ambiguity, because you typically accumulated, or the robot accumulated, a large uncertainty in its pose, and so it can be at several locations, and you have several possibilities for making data association. And you always also have the effect that it may be that you haven't returned actually in the same area you think you are, but you came to another area which looks exactly the same than the area you have been here. Who knows? You just complete symmetry. So two identical copies of this building and the corresponding green in front of it. You drive around, you come back, depending on the uncertainty you have. It can be the case if you simply are at another building which looks exactly the same than the place you've seen so far, but it's in a different location. So it's pretty hard, sometimes impossible, to actually make the data association. You can often say it's more likely that this is the case, that A or B is the case, but still there's some possibility that you end up in a different place which just looks the same. After a robot closes a loop, that means it re-enters already known areas and makes the correct data association between its observations and the landmark it has seen so far. It typically dramatically reduces the uncertainty in its own pose estimate and in the estimate of those landmarks. So you have a sport example over here. So the robot started somewhere over here, drove around, and this is the trajectory it took. This is the current position of the robot, and this is the uncertainty of the landmark. So you see the true landmark is kind of this guy over here, and the cross is the mean estimate. And then the robot reobserves the next point in time those landmarks over here. So it kind of closes the loops, revisits part of the environment as seen so far, does the update step, does the update, and now you can see that all the uncertainties here decrease because those landmarks are now correlated, and this uncertainty is kind of propagated backwards. But you can still see that the uncertainty here is somewhat bigger because they are further away from the loop closing point. So also the uncertainty here, down here, show it like this, you can see that it shrinks down here, but doesn't shrink that much at the position where you're close to the loop closing point. The reason for this is that between the correlations of the robot's pose, so all those landmarks are correlated with the robot's pose, but the further, the closer you have seen that and the less uncertainty the robot accumulated while moving, the higher this correlation is. Here another example where you can see here a map of the environment of the robot driving around, observing those features, and what you see here is a correlation between the individual landmarks. So while the robot is moving around and around and around, it accumulates these the correlation, get this correlation matrix. And this correlation matrix actually, so it's kind of a normalized covariance matrix. So the darker the value, the higher the correlation between values, and the smaller the value, the smaller the correlation. What you can see here is this kind of checkerboard pattern. And this means that, so some of you know that because one of the famous exam questions to explain that. This checkerboard pattern here tells you that the x locations of the individual landmarks are strongly correlated, and the y locations of the landmarks are strongly correlated. So if you would fix, let's say, the location of this landmark, if an oracle tells you this landmark is at a certain x location, you perfectly know the landmark locations of the x locations of all other landmarks, but you don't know basically nothing or very, very little about the y location. If you fix the y location, the same the other way around. So there's a strong correlation between the x locations and the y locations of the landmarks. You have kind of 2 degrees of freedom. If you fix one, you still have another degree of freedom. But in the end, what you're having here is you have a probability estimate about the landmark locations, and you have in a global reference frame 2 degrees of freedom. You can actually move the thing around the xy space, and still. The correlations, so the relative locations between the landmarks are known, but you don't know where they are absolute in space. Okay, again, a loop closure reduces the uncertainty in the estimate of the robot and in the landmark estimate because they're correlated. And so one thing is, using this property can be exploited in a way, for example, also to control a robot. So how should a robot move through the environment to build accurate maps or maps with low uncertainty? So you can explicitly generate loop closing commands in order to kind of close a loop, reduce the uncertainty before you continue. That's something we will not look into here, but this is something which is kind of an active SLAM system. If you think about this difference between active and passive SLAM, we briefly discussed in the first lecture. So a passive SLAM system assumes everything is steered. An active SLAM system may say, hey, let's actively go there and reobserve this part of the environment in order to potentially close a loop and kind of reduce the uncertainty in our estimate. On the other hand, it should be noted that doing a wrong loop closure, so doing the wrong data association, can have a very, very bad impact on your estimate, and typically leads to filter divergence, because you simply get an observation which can be far off from reality, and this leads to inconsistent estimates. So if you, this relates to what I've said before, in the limit, so if you run your mapping process, your landmark estimates get fully correlated. So this is one way for visualizing this. So the bigger the connections between landmarks, the higher the correlation between them. And this is sometimes you find it illustrated in this way, that everything gets correlated. Or you can see it in this matrix form, as I said before, if you plot the correlation matrix, that you see these dark entries. And you can even see that you have some patterns in here. So this is a matrix which is a little bit darker than the rest. So here's a pattern, here's a pattern, small subblocks. It means there are some subblocks which are stronger correlated than the rest. You can see this, for example, if I move in this part of the environment for a long time, then I move there, map there for a long time, in like 2 different rooms, they have a stronger correlation in the rooms than among the rooms. You can actually see some of those patterns in this correlation matrices over here. The other thing you can observe is that the uncertainty of the landmarks decreases over time. So what this plot shows is here the determinant of the individual uncertainties of the landmarks. Whenever you observe a new landmark, it's kind of initialized here with the maximum with high uncertainty, and then it actually decreases over time. So the more you observe, the more certain you get about the state of the landmark. So your observations kind of don't hurt. Even if your observation is very, very, very noisy, it may not contribute anything, but it doesn't hurt you as long as you don't have a systematic error. But so the more you observe, the more the uncertainty about the location of the landmark decreases. It decreases and decreases and decreases. However, it doesn't necessarily decrease to 0, because the uncertainty with which you can actually measure landmark location depends on your initial uncertainty. So if you had initial uncertainty in the beginning, you can measure as often as you want. You won't get more certain than your initial uncertainty, which also makes sense. In the end, you just estimate where the landmarks are relative to each other, but you do not know where they are globally. If you start with a 0 uncertainty in the beginning in your own reference frame, you may be able to bring them down to 0, actually close to 0. So you have some motion uncertainty always in there, depending what you observe at the first point in time. So typically, you have some kind of remaining uncertainty in the location of the landmarks, which is typically very hard to beat or impossible to beat, depending on the initial uncertainty you have. But the initial uncertainty is definitely a limit that you can't beat. Okay, now I have a few examples of kind of standard data sets. So this is an example of one of the first EKF SLAM data sets has been recorded at the Victoria Park at the University of Sydney by Jacobian Robot and his team. So you can see here one of those cars, and there was a laser scanner here mounted on top, and they were driving around with this car. A small video which shows that. Okay, you can see a small camera mounted on the roof. This is a laser scanner here in front, which observes the environment, and they have a small, simple tree detector running. So they were able to detect trees and generate this range-bearing observations of the tree. So relative observations from the current location of the car to the trunks of the trees. We just kind of extracted circles and estimated the center of the trunk of the tree. And if you do that, you come up with an estimate which looks like this. So the red thing here shows the trajectory of the robot, and you have here the estimates about the landmark locations. You can actually use this and overimpose this to a satellite image. If you do that, you can end up with something like this. So this is here always the trunk of the tree and its corresponding uncertainty ellipse. You can see that some are far off, so these are potential errors. But you can see me in this kind of, I'm not sure what was actually plotted here, but it was 1 sigma, probably 2 sigma bounds of the uncertainty. And sometimes trees are not recorded at all because there has been no observation. Sometimes it may be even the case like this one over here where it's unlikely that this is data association error. It may be that some person was standing here or there was something in the environment which caused a reflection in the system, determined that this could be a tree. Another data set is, which is often used for evaluation, is the tennis court, written there, of John Leonard and Matt Walter. The nice thing is here that these courts are very precisely measured for tournaments, so you have a very, very small error in these tennis courts. And so they use these, whatever the English term for this guy is, I have no idea, I'm sorry for that. The thing you use to jump over when you do running, so Bodenlauf in German. You place them in the environment, and so they know not at a very, very high precision where the things are actually placed in the environment, because you know the size of those courts very accurately. And so they could drive around with the robot, detect those poles over here, and then actually compare the estimate to the ground truth estimate. The ground truth, which is, let's say, quite precise, not perfect. You can actually see how the thing here nicely resembles the courts you have seen actually here. And these are 2 examples for data sets. So the Victoria Park is kind of, I would probably say, the most famous data set which has been used for SLAM. It's around since a very long time. It's one of the bigger data sets, and whatever paper you find on at least EKF SLAM, if it does something with features, it's a quite likelihood that the Victoria Park data set appears in there. And the other data set here hasn't gained that much visibility, although it's also a nice data set because you have this pretty good estimate about the ground truths. Okay, so a few words on the complexity. As I said before, the complexity of the Kalman filter is quadratic in the number of landmarks we have in the environment per update step, and it's cubic in the dimensionality of the measurement function, although this is not the kind of interesting part in the context of EKF SLAM. So the quadratic complexity is the thing which really hurts. So if you want to build the map of the whole environment, it's a cubic complexity because you typically observe a limited amount of landmarks throughout the environment, so it's roughly cubic. Memory consumption is quadratic, and so this is one of the reasons why the EKF becomes intractable for really huge, large-scale environments. So you can do estimates for medium-sized environments, but typically you can't do it for large-scale environments. So actually, this n by 3 is, of course, it depends on the length of your trajectory. So if you travel for ages through the environment, then this has to be the length of the trajectory, have the quadratic updates there. So a few words to sum that up. So the EKF was actually the first, let's say, real solution to the SLAM problem with the full probabilistic treatment. There exist convergence proofs for the linear Gaussian case. The problem is, in reality, if you have nonlinearities, the system can diverge based on the nonlinearities. So if your nonlinear function is really badly behaving, your Taylor approximation maybe can be a too bad approximation to actually come up with a good estimate of the environment. So if you're really bad nonlinearities, this actually can lead to problems. The other problem is that these systems can only deal with a single mode. So we just have a Gaussian distribution and not multimodal distribution. And especially in the case if you have ambiguities in the data associations, that's also one of the questions that came up before. If you say the robot is either here or here, that's something the system cannot handle. So what you would need to do is you could copy your Kalman filter and continue running one Kalman filter where you say this was the correct data association, and another Kalman filter when the other data association was right, but then you kind of start duplicating your model. So there's no way in the Kalman filter itself to deal with multiple modes. And so far it has been applied to, let's say, kind of medium scale size. Also, if you have the possibility to kind of perfectly engineer your environment, let's say you can place perfectly distinguishable features in the environment for an industrial application, for example, it can also be a good choice to run that Kalman filter, because if you can engineer an environment, you can make sure that there's no ambiguity in the data association. Why not use it? And if the environment is not too huge, it's a well understood technique. It's been investigated for, yes, since the beginning of the 90s. Successful systems have been around in the 80s. And there are also a couple of approximations of the Kalman filter to deal with the complexity of the system. For example, splitting the map up into small local maps, or into local maps, and then updating only the local maps that the robot is currently in. You can use this to kind of bound the complexity to the size of your local maps, but you kind of, at least in the most basic way, ignore the cross correlations between landmarks that between different submaps. Or you have to put another estimation layer on top of that, which then tries to approximate those correlations. And there are kind of hundreds, if not thousands, of approaches that try to fix that the computational complexity of the Kalman filter by introducing some approximations and how to kind of fix it with losing as little as possible. So there are approximations that you can do certain things more efficient today, but kind of in the plain system as was presented here, it's not applicable to large-scale environments. Most of the slides I created here, you can find the background material in the EKF SLAM chapter of the Progressive Robotics book, chapter 10. All the algorithms are in there. If you're working with the first edition of the book, check the errata website. There's quite some minor difference between what's on the slides and what's in the book, because it's partially an error in the book. And so these versions are hopefully the correct ones, unless I put a typo in there. But if you experience a difference between what's on the slides, what's in the book, look at the website, progressiverobotics.org. There's an errata page. You can check if it was my error or the error of the book. Especially the first printing had some errors. Okay, so we kind of finished today EKF SLAM, and I hope you understood that. If you need more information about one part of that, visit me in my office, ask your teammates, ask them the exercise, Nicola or Rainer, and so hopefully you're able to implement the vanilla EKF SLAM system within the next 2 weeks. There's a framework which will be provided to read and log files. We provide some log files, some plotting mechanisms that you can use in order to build your own EKF system, and you mainly have to do the prediction and the correction step, and the rest is kind of handled on our side, so that the implementation work shouldn't be too much and you can actually concentrate on the most relevant parts. Are there any questions?
Short question. If the robot should solve such tasks like go from your current position to gather spawn, it could use an additional map with some exact precision or length or something.
I haven't fully understood the question.
Yeah, we have see that the robot is driving around
Yep.
a little bit randomly, and if it should use solve such tasks like go from a current position to pebbles or to the goal, it should use an additional map with some information or something.
So you need to allow, in general, the path planning or the motion planning system to find its way. So you can do that by either providing some rough sketch map or very abstract map, or something you can download from OpenStreetMap or from Google Maps to have a very rough reference where to go. You may provide with GPS, which has, say, significant uncertainty, especially in urban environments. But you know at least roughly where to go, but then you can build up your accurate map. So this is kind of a question which I would not necessarily attach to the SLAM problem here, more to the question on how to navigate and how to move. Of course, you can say you should explore the environment around you and come up with a map, so you may see a robot randomly exploring the environment or going to places where it hasn't been so far. At some point in time, it will reach the target location, but this may be very short time. So typically you need to provide, or it's helpful to provide some external information for the navigation system that the robot should know where to go. But this is strongly depends on the application, and it's hard to actually put that into the SLAM algorithm. So what some approaches do is they kind of try to select actions that aim at minimizing the uncertainty in your belief. belief. So where should I go to minimize the belief of the uncertainty in my belief? But if you have some kind of external task or what to do, you kind of need to encode this task knowledge into the system. It's in the decision making at some point.
But that one that goes from here to Patterson, that was a SLAM.
Yes, so it was kind of a two-layered approach. So on the one hand, you had you can joystick the robot at some point to build a map, and then you can actually navigate in that map you build once. Also, the possibility of kind of extending the map. If you know parts of the map, you can actually do some kind of exploration actions. But it may be that this exploration action actually fails, and you have to kind of go back, try an alternative path. So we had some heuristics in there, but there was some background knowledge required. Or actually a map built by actually steering the robot once and then kind of revisiting that map, localizing that map, navigating in order to the navigation task. But the first point in time, at least in the system, how we presented it here at Freiburg, it had a map that it previously recorded.
How we detect that the landmark we currently observe, we did it for the second time or the third time? Is it the same landmark we observed before?
Yeah.
How we did it?
So the data association. Your question was
Yeah.
how we do the data association, or?
Just how we detect this landmark is the same landmark and we observed before and we reduce the uncertainty.
Exactly. So this is exactly the data association. How can we determine that the landmark we currently see corresponds to the landmark J in the environment? Oh, that's the question, right? Okay. So
we observe it for the second time or in a loop closure.
Yeah, exactly. It doesn't matter when, at every point in time when we see something, we need to make the data association. The only difference is that in the loop closing case, we typically have a higher uncertainty about where the robot is relative to the landmark. So there are different ways of doing this. The easiest, most straightforward way, if you don't have any further information, is to do a nearest neighbor assignment. So you observe a landmark. So you might give my coordinate estimate of the landmark is here. What are landmarks in my map that are close to this one, where which could correspond to the one I see? If I don't have any further information, that's kind of the thing people typically do. If you say, if the probability that this observation corresponds to this landmark, which you can do because you have a full belief about it, is, let's say, below 0.1 probability, say it's a new landmark. So you have some gating function in there which tells you, I create now a new landmark or I create an old landmark. And so you may come up with creating a new landmark, and later on you may have two landmarks exactly the same location, which may be an indicator that this is actually the same landmark, but it's typically better to, or it's not that critical to establish a new landmark, although in reality this was just a single one. More critical is making the other way around. So say, this landmark, this observation equals to this landmark, although this is not the case. This is typically more critical for your system. If you have further sensor information, like visual information, which can provide you whatever SIF features, SURF features, whatever features about the environment, or some other technique for doing place recognition, you can actually perform much better than this kind of stupid, straightforward nearest neighbor association. But this depends on the application. In terms of doing nearest neighbor associations individually, you can also kind of use this for solving or using solutions to assignment problems to say, I observe multiple landmarks because I kind of drive a little bit in the environment. I kind of build local maps and do the data association a little bit delayed to fix this only if whole submaps corresponds to what I've seen before. So there are certain tricks of delayed data association and things like this, which improves the situation, but still. If you come to an environment which looks basically identical to what you've seen before, also it's a different place. That's really, really difficult to handle, especially for a system which has to commit to one data association, which is the case for the Kalman filter. So you can't have multiple data associations. And unless, as long as you can only use one data association hypothesis, cannot have multiple in parallel, you're trapped at some point.
Are there any reference for this data association issue in this?
Yes, of course they are. Actually, we'll look into data association at a later point in the lecture as well. So there will be, there's things like the standard nearest neighbor, there's this joint compatibility branch and bound. There are different techniques which you can use in different place recognition techniques that people develop, which you can use to support data association or to do data association. And some of them we will actually look into in that course, but kind of a little bit later on in the course of the second half of the course. We'll look into kind of the real data association. Okay, any further questions? Okay, Ben. Thank you very much, and see you next week.
It looked kind of okay.